What is the most interesting number in the world? Hi, I'm Joe, and this little guy, this is Steve. I'm a math student at the University of Bath. Steve, on the other hand, has never studied a day in his life, but I'm sure you won't mind his cuteness sticking around for today. Oh, you're so cute. Yes, you are. Yes, you are. There are plenty of numbers that we see a lot in mathematics that have a lot of uses. 1, 2, 100, 420, and so on. I'm sure that you have numbers that are special to you, like your age, birthday, or house number. Some people have lucky numbers or favorite numbers. For me, both of those are 7. But how can we say if a number is interesting? And if so, how interesting? This brings me to the interesting number paradox, thought up by number theorists for centuries, and first referenced by Edwin Beckenbach in 1945. This paradox attempted to separate each positive integer as either interesting or not interesting, but in doing so managed to prove that there are no not interesting numbers. The proof is by contradiction and goes as follows. If there exists a group of not interesting numbers, then there must be a smallest not interesting number. If k is the smallest not interesting number, that is something interesting, and now k is interesting. This means that our group of not interesting numbers doesn't have a smallest entry, and therefore must be completely empty, and that all numbers are interesting. There's something quite wholesome about that, isn't there? Each number may seem more or less useful, but each number has something special to it. It is interesting, and they're all special in their own unique ways. Nah, that's boring. If we know that each number is interesting, then what if we tried to do the opposite of Beckenbach and found the most interesting number, like a huge Venn diagram of different number facts, and we try and find the integer that fits right in the middle? Will we get a similar result, or can we make a new paradox? Let's start by establishing how to quantify interestingness. There are definitely some categories that we can include. Prime numbers, numbers with 2 factors. Square numbers, the same number multiplied twice. Cube numbers, the same number multiplied 3 times. Triangle numbers, the sum of the first n integers. Or perfect numbers, where all factors add up to itself. I'm sure that you can think of some categories that we could add in. And in fact, there are an incredibly large number of various sequences of unique types of numbers out there. But luckily for us, there already exists a tool out there to speed things up. This is the Online Encyclopedia of Integer Sequences, or OIS. It is a large collection of sequences found in maths that was founded in 1964 with over 390,000 entries. And we're going to use this to find out which number has the most interestingness. To simplify things, let's start with the numbers up to 100, and the core sequences of the OEIS, which act like the building blocks of all sequences. We can count which number appears the most times. Each time a number appears in one of these sequences, that will increase its interestingness by 1. So if a number was only square, a power of 2, and in the Fibonacci sequence, that would have an interestingness of 3. Pause the video and take a guess at what you think will rank as the highest interestingness. This is a spreadsheet of all the core sequences according to the OEIS, and by going through all the core sequences and adding the interestingness of each, we get this table. And if we further rank them by their interestingness, we find that 1 is the top of the leaderboard, with 2 in second, and 3 in third. Pretty interesting, I say. Did you get it right? One thing to note is that even though not all of our integers are in the same order, there is a clear trend of smaller integers having a higher interestingness. Do you think this is a satisfactory conclusion? Let's try and push it further. We can add weights to each sequence based on rarity, so that the rarer a particular sequence is, the more interesting it is. Weight is calculated by the total number of numbers, 101, divided by the frequency of the sequence. For example, there are 25 primes under 100, so the prime sequence would have a weight of 4.04, or on average, 1 in 4.04 numbers between 0 and 100 are prime. Our interestingness now follows this formula. Interestingness equals the sum of the weights of the sequences that the number is in, where we use a piecewise function to separate whether a number is in a sequence or not. Do you think this new formula will change our ranking? calculating our new interestingness via the same method but our new formula gets us this table. Now we can see some differences, but 1, 2, and 3 rank in first, second, and third, and we arrive at a similar conclusion as before. If we check out the bottom end of our tables, this further implies our hypothesis. Now, let's add another variable to our model, which we'll call count. Adding to our previous formula, the count variable, c, will represent if a number appears multiple times in a sequence. We will multiply each term by c and then sum over all the sequences. Let's make a new table based on our updated formula and rank them again in order of interestingness. And here we see a change in our top 3. The 0 has taken the second spot. But this updated model has only further added to our hypothesis that smaller numbers have a higher interestingness. We find again the higher numbers in our set have the lowest interestingness. But of course, we are only looking at a very narrow list with a narrow set of sequences. We could expand our search to see if any larger numbers have a high interestingness. However, what issues would we have if we expanded our search? Pause the video and try to think of some dilemmas that we would face. First of all, with the number of sequences, this would take an awfully long time. Possibly with a specific computer program we could calculate interestingness on a wider scope, but new sequences are discovered all the time, with the OEIS adding an average of 30 new sequences a day. But our main problem lies in infinite sequences. Many of the OEIS sequences are infinite, and so calculating frequency becomes tricky. You could calculate the average proportion of entries in the sequence out of the integers, but with many infinite sequences, this can be unknown, or even have a weight of infinity as you tend to infinity, such as A011557, the powers of 10. Between 1 and 10, the weight is 5, between 1 and 100, the weight is 33.3, between 1 and 1000, the weight is 250, and so on. However, in 2009, Philippe Guglielmetti tried to rank the interestingness of each number on a wider scale. Note that Guglielmetti only counted for appearances in sequences and did not factor in rarity. So this graph is based on our simple model. This graph became known as Sloan's gap, after the clear gap between the blue uninteresting numbers and the other numbers, red primes, green powers, and yellow highly composite numbers, which means that it has more proper divisors than every integer less than it. If you wish to find out more, there is a lovely number file video about Sloan's gap that I will link in the description. But Guglielmetti's experiment still gave us the same conclusion. The smallest integers are the most interesting, and the single most interesting number is 1. Contrary to the famous De La Soul song from the 80s, 1 is the magic number. But interestingness is not a formalized metric, and ultimately it was a fun thought experiment to see what classes as interesting. But we only looked at integers. What about fractions, irrational numbers, or numbers that don't even exist? But in my heart, all maths is interesting. And if you're interested, I could be the one you need. Okay, cut it. We need to wrap. I need to go home.